So here we have our evaporator coil. So the refrigerant's going to be evaporating, or actually boiling. We're going to talk about that later on. But what we need to know now is we had an immediate pressure drop. So here we went from a high pressure liquid to a low pressure saturated mixture. We'll talk about saturated later on as well. So here, because we had a pressure drop, we also had a temperature drop. So now the temperature of the refrigerant is a lower temperature. There's a lot of places that actually cool with just simply a pressure difference in air. You can actually have a cooling effect just simply with the pressure difference. So what we're doing inside of here is dropping the pressure of the refrigerant, which is also dropping the temperature of the refrigerant. So blue is representing low pressure. And if you see, we're feeding this coil through 6 different locations. 1, 2, 3, 4, 5, 6. There's actually 6 of these little tubes. Remember, these are distribution tubes because this is my metering device. So we're distributing that refrigerant to multiple locations of this coil. Now this refrigerant runs back and forth across this evaporator coil. And all these tubes, these are called little U-bends or U-tubes, the original U-tube, but the refrigerant's going back and forth through this evaporator coil. The idea is we're sending all that refrigerant, there's a lot of surface area, a lot of tubing. A lot of that tubing's touching a lot of this aluminum. So there's a lot of surface area, the second law of thermodynamics. The refrigerant is a lower temperature than the air. So the heat's going to leave the air and go to the refrigerant. Since there's a lot of surface area and it's made of aluminum and copper, which is great for transferring heat, we can very effectively move heat. Second law of thermodynamics go all in here. Now as we take heat away from the air, the temperature of the air drops. I've taken heat energy out of the air and put it into the refrigerant. So the air comes out cooler. So we're only cooling the air by removing heat from it. That's the first law of thermodynamics. But it's essential that we have airflow across this evaporator coil. In this case, our blower is up here above it, and we're actually pulling air across it. And the other cases, like the gas furnace, the coil is on top, and I'm pushing air across that evaporator coil. It doesn't matter if we pull air or we push air, as long as we get air through the evaporator coil. There's many different styles of evaporator coil, but here's another example. Just these little bitty tubes, and just like we had with the condensing coil, it's a heat exchanger. Here we have the tube and fin style. So the refrigerant, as it's running through these tubes, it's low temperature, low pressure, and it's lower than the temperature of the air. The air is flowing through these fins on the other side, and we're taking the heat out of the air through this type of heat exchanger to the refrigerant. So the heat leaves the air, goes to the refrigerant, the temperature of the air drops. We push that cooler air back into the house. Now there's a whole lot more going on with this. We're going to talk about that soon, but let's just first learn the basics. The refrigerant here is absorbing heat. It's absorbing heat away from the air. It's essential that we keep our fan running so that we move air across the coil. Because if we want to absorb heat from the house, we need to absorb it from the air. So having that fan run is essential, and many times it's overlooked. If we look in other cases, we also want to make sure that coil stays clean. Here's an example of an evaporator coil on the underside that's extremely dirty. This does 2 problems. Number 1, it's blocking airflow. Number 2, the dirt is working as an insulator. So insulators prevent heat transfer. It slows the second law of thermodynamics. So now I'm blocking airflow, so that means there's less heat coming across it. And also with the dirt, I'm insulating the coil, so I'm slowing the heat transfer down. This makes this evaporator coil less effective. I'm not transferring heat from the air to the refrigerant like we need to, and it's a very big problem. So airflow is essential. For a refrigeration cycle. We're going to be talking about airflow a little bit later on, but we can't really do anything with the refrigeration cycle if we don't have the proper airflow. Now we talk about airflow and these evaporator coils, but there's also other kinds. There's many different types of evaporator coils. This particular one came out of a 1950 Coca-Cola Coke machine, registered trademark, no affiliation with them. But the idea is same thing. The temperature of the refrigerant is lower than the temperature of the air. So the heat leaves the air and goes to the cooler refrigerant. As the air cools off and travels around the soda cans, the heat leaves the soda, goes back to the air. The air warms up. There's this little fan here that's pulling air across this coil. The heat leaves the air, goes to the refrigerant. Air cools off, goes back around, and the cycle continues. So thermodynamics is a huge part of what we work with. But it doesn't just have to be with air. We can also cool many other things, such as water or glycol or beer or stones. You ever heard of cold stone creamery. We're actually taking heat out of the stone. That then takes heat out of the ice cream. Some of the older refrigerators had coils that looked something like this. This is actually your evaporator coil. The refrigerant actually flowed through these fins here, and this is where your ice tray actually went, and it would take the heat out of water. And if you take heat out of water, it'll turn into a solid. Also, there's a little bit of fan that moves around, and this would cool the rest of the freezer, as well as it had a damper that controlled how much air went to the bottom side to control the temperature of the box. We'll get into refrigerators a little bit later on, but I want you to understand that it's still going to have an evaporator. We're still going to be absorbing heat. This guy here is still absorbing heat, and this one here is still absorbing heat. So here we have another style of evaporator coil, a different brand, and there's a whole lot more of these little bins here. We call this a W coil. This particular brand uses a whole lot more of these little bitty tubes, but the idea is use them in less space. So if we were to pull that coil out, it would actually look something like this. Notice it's not painted, but all this would be low pressure. We would draw this in blue. So the air is traveling through all of these different pieces. If you notice, this side right here has a significant amount of dirt on it. This side has a lot of dirt, but this one doesn't. That tells us we had an airflow problem. The air wasn't flowing through this evaporator coil properly. But also, this is really, really bad. This definitely needs to be cleaned. What happens is this has caused damage to the compressor outside, and we'll talk about how that ties in later on as well. And let's not forget our drawing. So we have our metering device. Now we're going to change to blue. Blue represents low pressure. So what we're going to do is go back and forth as we draw, and this is going to represent our evaporator coil. And these little back and forth represents those little U bends that you saw, those little U tubes. So we're going to write over here evaporator coil. And what that evaporator coil does is absorb heat. And what we're going to do is label on this inside, because this is the inside unit. Our metering device is located right near the evaporator coil, so both of these together are inside, and our compressor and our condensing oil unit is located outside. Now we're going to add a whole lot more stuff to this evaporator. It's not just low pressure, there's a lot more that goes into it. Stay tuned, we're going to get there. Practice these words, make sure you know all this vocabulary, and we're going to continue on.